19.3 Latent Heat. In this lecture, we will explore the fundamental concepts of phase changes and latent heat. Our discussion will cover how energy transfer impacts internal energy without changing temperature, the specific definitions of the latent heat of fusion and vaporization, and a detailed analysis of the energy required to convert ice into steam. We will also examine the interesting phenomena of supercooling and superheating, which occur when substances do not transition between phases at their expected temperatures. It is a common observation that adding energy to a substance usually increases its temperature, but this is not always the case. When a substance undergoes a phase change, such as melting or boiling, the energy transferred into the system does not change the temperature. Instead, this energy is used to alter the internal energy of the system by breaking the bonds between molecules. For example, during boiling, the added energy increases the intermolecular potential energy as molecules move further apart to transition from a liquid to a gaseous state. This means that while you are heating a pot of boiling water, the temperature remains constant until the phase change is complete. We define latent heat, which literally means hidden heat, as the energy required to change the phase of a specific mass of a substance. Mathematically, latent heat equals the energy transferred divided by the change in mass of the higher phase material. We can also express the energy required for a phase change as the product of the latent heat and the change in mass. It is important to note that the change in mass refers specifically to the material existing at the higher temperature, such as water when considering an ice-water mixture. The value of latent heat is not a universal constant. It depends specifically on the type of substance and the nature of the phase change being performed. There are different types of latent heat, depending on the specific phase transition. The latent heat of fusion is used for transitions between solid and liquid states, while the latent heat of vaporization applies to transitions between liquid and gas. Interestingly, the energy released during condensation is numerically equal to the latent heat of vaporization, and the energy released during solidification equals the latent heat of fusion. When performing calculations, the signs are critical. We consider the energy transfer to be positive if energy enters the system, such as during melting or vaporization. Conversely, the energy transfer is negative if energy is extracted from the system, which occurs during freezing or condensation. To understand how these concepts apply in practice, let us analyze the energy required to convert 1 gram of ice at -30 degrees Celsius into steam at 120 degrees Celsius. This process is divided into 5 distinct parts. First, we warm the ice to 0 degrees, requiring 62.7 joules. Second, we melt the ice at a constant 0 degrees, which takes 333 joules. Third, we warm the resulting water to 100 degrees, requiring 419 joules. Fourth, we vaporize the water at a constant 100 degrees, which takes a significant 2,260 joules. Finally, we warm the steam to 120 degrees, adding another 40.2 joules. This graph illustrates the relationship between the temperature of the system and the total energy added during the transition from ice to steam. You will notice 2 distinct horizontal plateaus labeled Part B and Part D. These plateaus represent the phase changes of melting and boiling, respectively. During these stages, the temperature stays exactly at 0 degrees or 100 degrees, even as we continue to add energy. The diagonal lines, labeled A, C, and E, show the periods where the substance exists in a single phase ice, water, or steam, and the added energy results in a steady increase in temperature. The long plateau for vaporization highlights just how much more energy is needed to turn liquid water into gas compared to simply warming it. The high latent heat of vaporization for water has significant practical implications, particularly regarding safety. A great deal of energy is required to turn water into steam, and that same energy is released when steam condenses. This explains why a burn from steam at 100 degrees Celsius is much more severe than a burn from boiling water at the same temperature. When steam hits your skin, it releases a massive amount of energy as it condenses into a liquid while staying at a constant 100 degrees. In contrast, liquid water at that temperature immediately begins to drop in temperature as soon as it transfers energy to your skin, resulting in less total energy transfer. Sometimes substances do not change phase at their standard transition temperatures. Supercooling occurs when liquid water drops below 0 degrees Celsius without freezing. This happens in very clean containers, where there are no disturbances or nucleation sites to start the ice formation. If the water is disturbed, it freezes instantly and releases energy that brings the temperature back up to 0 degrees. Similarly, superheating occurs when water rises above 100 degrees without boiling, which can lead to explosive bubble formation if disturbed. This principle is used in commercial hand warmers, which contain a stable, supercooled solution that solidifies and releases heat when you trigger a small disk inside the pouch. Let us look at a calorimetry example, where we find the mass of steam at 130 degrees needed to warm 200 grams of water in a glass container from 20 degrees to 50 degrees. We use the principle of conservation of energy, where the energy gained by the cold water and glass equals the negative of the energy lost by the hot steam. The steam must first cool to 100 degrees, then condense into water, and finally cool as a liquid to 50 degrees. By accounting for the energy in each of these three steps, and setting them equal to the energy gained by the container, we find that 10.9 grams of steam are required. If the final temperature were higher, even more steam would be necessary. In summary, we have learned that phase changes occur at a constant temperature, despite a continuous transfer of energy. We use the concept of latent heat to quantify the energy involved in these transitions, calculated as the product of the latent heat constant and the change in mass. The latent heat of fusion applies to the solid-liquid boundary, while the latent heat of vaporization applies to the liquid-gas boundary. When solving complex calorimetry problems, it is essential to account for both the diagonal sections where temperature changes and the horizontal plateaus where the phase change occurs at a constant temperature. To wrap up, consider these review questions to test your understanding. First, why exactly does an ice-water mixture stay at 0 degrees even when you add heat, and what is happening to that energy at the molecular level? Second, explain why the definition of latent heat specifically uses the mass of the higher phase material. For example, if you were dealing with a condensation problem, how would you determine the value of the change in mass to ensure your signs and energy calculations are correct? Reflecting on these points will help solidify your grasp of thermodynamic phase changes.